This is a talk on the paper Circuit Lower Bounds from NP-Hardness of MCSP under Turing reductions. And I'm Rahul Santhanam, one of the authors of this paper. I'll be guiding you through the presentation. This talk is about the minimum circuit size problem, MCSP. So this problem is the focus of this talk. It's a fundamental problem in complexity theory, where you're given as input a Boolean function f on n bits, which is given by its truth table of size 2 to the n. We'll be using little n to denote the input size of the Boolean function and capital N to denote the truth table size, and a size parameter s. And the output for this problem is yes if the Boolean function f has circuits of size at most s. MCSP is important for several reasons. It has relevance to many areas of theoretical computer science, including circuit complexity, learning theory, cryptography, proof complexity, and so on. And there's been quite a lot of recent work on the problem demonstrating its impact. From a practical point of view, the problem is interesting as well because it captures the question of circuit minimization, which comes up in hardware design. There are several variants of MCSP, which I'd like to mention. So MCSP, as defined before, S, the parameter, is given as part of the input. You can make S a function of the input length, and you can define a parameterized version, MCSP of S, which asks whether there's a circuit of size at most S of n for some fixed function S. Instead of asking whether the input Boolean function has a Boolean circuit of a certain size, you could ask about circuits from a certain class, capital C. So this could be, for example, the class of DNFs, the class of constant depth circuits, the class of constant depth circuits with parity gates and formulas, and so on. For each of these classes, there's a corresponding problem C MCSP. There are approximate versions of MCSP where you want to compute the circuit size approximately to within a certain factor. So G approximate MCSP asks what the circuit size of the input Boolean function f is to within a factor G of n, where G is a pre-specified function. And then there's, for example, MCSP with partial truth tables. So instead of giving the complete truth table of a Boolean function, you might be given a partial truth table with zeros, ones, and stars. And you might ask whether there's a total Boolean function f with circuit size at most s that is consistent with this partial table. So several of these variants have been studied in detail, and there's an interesting network of relationships between them that I don't have time to go into, but it's just sort of an indication of the richness of MCSP. So the most basic question about MCSP in complexity terms is how hard is it? So one easy observation is that MCSP is an NP. And in order to see it as an NP, you can just guess a candidate circuit C for the input Boolean function f of size at most s and verify that the circuit C computes f correctly. So why is this verification polynomial time? It's polynomial time because we're given the entire truth table of the Boolean function f. So it's capital N bits, there's capital N possible inputs of size little n, and verifying on any given input of size little n takes time close to s. You need to compute the circuit C on that input and check whether the corresponding bit in the truth table is set right. And you need to do this for each of the capital N bits. So the total time for verification is n times some polynomial in little s. And since little s is at most capital N, that's polynomial in capital N. So is MCSP in polynomial time? Well, that's considered unlikely. The natural proofs framework of Rasparov and Rudich implies that under standard cryptographic assumptions, the assumption that one-way functions exist, MCSP is not NP. And this was observed by Kabanets-Cai in their seminal work for studying the minimum circuit size problem in detail. But a major open problem is MCSP NP complete? MCSP is an NP, MCSP is not NP. So a natural conjecture is that MCSP is NP-complete. The vast majority of natural computational problems in NP are either known to be NP or known to be NP-complete. And there are a few exceptions which are noteworthy. There's problems used in cryptography, such as factoring, discrete log, certain lattice problems. These problems often have features such as random self-reducibility. They're statistical zero knowledge quite often. So there are problems of this kind, which are neither known or believed to be NP and are also not believed to be NP-complete. There's graph isomorphism, but in this case, we do know a quasi-polynomial time algorithm due to Babai, and there are many researchers who believe that this problem is in polynomial time. And then there's MCSP and its variants, where there's cryptographic evidence that the problem and its variants are not NP, but we also don't know NP-completeness results. And it's reported that Leonard Levin, in fact, delayed publishing his NP-completeness result because he wanted to show that a version of MCSP, of circuit minimization, was NP-complete, and he was unable to do this. MCSP is perhaps an outstanding example of a computational problem which many complexity theorists believe to be NP-complete. I, for example, believe it to be NP-complete, but it's not known to be. So why this special difficulty of showing NP-hardness for MCSP? Why is it so hard to find a reduction from satisfiability to MCSP? Intuitively, it's because the instances of MCSP, especially the no instances, behave in a sort of random fashion. And in order to construct a reduction from SAT to MCSP, you need to encode SAT into MCSP. And it's quite hard to encode a given set into something that looks random. That's very, very high level intuition. And in fact, there's an analogy between MCSP and the set R sub k of Kolmogorov random strings, so strings that require Kolmogorov complexity at least NO2, say. It's known that that R sub k is undecidable, but it's also known that R sub k, the set of Kolmogorov random strings, is not hard for the RE sets with respect to many one reductions. And you can think of the question of NP-completeness of MCSP as sort of a scaled-down, resource-bounded version of this question, where MCSP is sort of a resource-bounded version of R sub k, and we're looking for a completeness result. And the question is there many one completeness, or might this fail to hold? So these are rather vague intuitions and analogies. Can we say something formal about the difficulty of showing NP-hardness? So there are indeed such results, and the pioneering result of this sort was a result of Kabanets-Cai, who considered the question of NP-hardness of MCSP under certain restricted kinds of many one reductions. So they looked at natural reductions to MCSP. A natural polytime reduction to MCSP is a many one reduction where the size of the output and the parameter depend only on the size of the input. Notice that if you have a reduction from some NP problem L to MCSP, then given any x that's an instance of L, you go to compute the output of the reduction. So the output is a truth table together with the parameter. And the naturalness condition means that the size of the truth table as well as the size of the parameter depend only on the size of the input. And this naturalness condition is indeed natural, as the name would suggest. All the standard NP-hard problems are hard also under natural reductions. And a surprising fact, and shown by Kabanets-Cai, is that if the minimum circuit size problem is NP-hard under natural reductions, then a circuit low bound follows, which is quite far from what we know how to show. It follows that E, the class of languages that are decidable in time 2 to the order n, does not have polynomial size circuits. And since it's been a long-standing open problem to show super polynomial circuit size low bounds for E, this suggests that NP-hardness of MCSP under natural reductions might also be hard to show. So I'll give a proof sketch for this result, just a proof sketch by picture. So suppose there was a natural reduction from SAT to MCSP. Suppose there's a reduction f that is natural from SAT to MCSP. So f is a natural polynomial time reduction mapping SAT to MCSP. What we will do is use the reduction f to generate in polynomial time, given some input 1 to the n and unary, we will generate in polynomial time the truth table of a function on order log n bits that requires super polynomial size circuits. And this is essentially equivalent to showing super polynomial size circuit low bounds for E. So how do we do this? The idea is very simple. We just compose the reduction f with an explicit construction of unsatisfiable formulas. So we just pick your favorite construction of unsatisfiable formulas of length n, some polynomial time construction of unsatisfiable formulas, and then given this unsatisfiable formula phi n, apply f to it to get f of phi n, which is a truth table together with a parameter. Now let's assume, just for the sake of this discussion, that the parameter is large. So the parameter is, say, n to the omega 1, where n is the size of phi n. Then we get really strong circuit low bounds for E, because we have generated in polynomial time from 1 to the n the truth table of a Boolean function that doesn't have circuits of size less than n to the some constant epsilon. So that means that E has some very hard functions. Of course, we need to justify this assumption that the parameter is large. And in order to do this, you need a case analysis. You need to consider the case where, for almost all input lengths, the parameter is small. And in this case, one can argue, using a different argument, that E requires large circuits. And then there's a case that for infinitely many input lengths, the parameter S is going to be large. And in this case, the argument that you've just given by picture works. So, following in the work of Kabanets-Cai, there have been several other results along these lines, showing that various kinds of reductions to MCSP from SAT would have strange, surprising consequences, hard to show consequences, or just don't hold. So, for example, Murray and Williams show unconditionally that MCSP is not NP-hard under D-log time projections. So D-log time projections are a very restricted notion of reduction, but already sufficient to capture most reductions that happen in the practice of theory. They also show that if MCSP is NP-hard under M reductions without the natural restriction, then we get a complexity separation X does not equal to ZPP. So we get a separation between the class exponential time and the class ZPP of languages decidable in zero-error polynomial time. And this is, again, a separation that we don't know how to show and that seems out of reach. So it indicates that perhaps showing any sort of NP-hardness result for MCSP under M reductions could be tricky. Hitchcock and Pavan show that if MCSP is NP-hard under truth table, namely non-adaptive reductions, then the same consequence follows. X doesn't equal ZPP. And it's natural then to ask, well, what about Turing reductions, adaptive reductions? Could adaptive reductions give more power and allow an NP-hardness result for MCSP to be shown, or are they also limited somehow? So that our work addresses this question, and we first need some setup. We need to define a couple of notions that are crucial to our work. We consider two restricted notions of Turing reduction that, like the notions that I've just discussed, seem to capture many reductions that occur in practice. So the first is the notion of parametric honest reductions. These are Turing reductions where, given an input x, the parameter of the output is the length of x to the omega 1. So given an input x, you could ask many queries to MCSP on that input. And the parameters for these queries could be different, but what these parameters all have in common is that they're all at least size of x to the epsilon for some constant epsilon. And then there's a notion of natural reductions, which generalizes the notion of Kabanets-Cai, notion of natural related Kabanets-Cai, to Turing reductions. So this is where both the output size of the truth table that you ask a query on, and the parameter depend only on the length of the input. So on an input of length n, you're only allowed to ask queries of truth tables of size, say m of n and parameter s of n. The truth table size and parameter are fixed as a function of the length of the input. Note that these two notions are incomparable, because in the first notion of parametric honest reductions, you could ask queries with different parameters. It's just that the parameter is constrained always to be large, to be a size of x to omega 1. While in the case of natural reductions, there's freedom, flexibility in terms of the size of the parameter. The parameter could be either small or large, but the parameter depends only on the input length. And so does the truth table size. So here are our results, very similar or analogous to the result of Kabanets-Cai. The first result is that if MCSP is NP-hard under parametric honest Turing reductions, then E does not have polynomial size circuits. The second result is again a circuit low bound under the assumption that MCSP is NP-hard under natural Turing reductions. So the message somehow is that either we need to use non-standard reductions, new techniques, new ideas to show the hardness of MCSP under Turing reductions. Namely, we need to use Turing reductions that are not parametric honest or natural, or we will be showing breakthrough circuit low bounds by showing an NP-hardness result. So, in order to discuss the idea behind the ideas behind the proofs of our results, just need to recall the Kabanets-Cai idea, because that's what we build on. So, recall that Kabanets-Cai showed that if MCSP is NP-hard under natural M reductions, then E does not have polynomial size circuits. And the idea was to use a natural reduction to generate the truth table of a hard function. First, generate in polynomial time an unsat formula phi of size n. Since phi is unsat and f is an M reduction, f of phi must be a negative instance of MCSP. And now there are these two cases. Since we're dealing with natural M reductions, the parameter depends only on the input length. So either the parameter is small for almost all input lengths, or it's large infinitely often. If it's small for almost all n, then we can use brute force search to solve SAT via the reduction in quasi-polynomial time. And it's well known that standard techniques in complexity theory give superpolynomial circuit low bounds for E from this, from such a quasi-polynomial time algorithm for SAT. And if it's a case of the parameter, the other case of the parameter S is large infinitely often, then f of phi is a truth table of Boolean function that's hard, that requires superpolynomial size circuits. And so we will get a Boolean function in E which requires large circuits, and we're done again. So that was the sort of case analysis in the argument of Kabanets-Cai. So first of all, why doesn't this generalize? It's faced to generalize even to natural one query reductions, let alone truth table or Turing reductions. And let me just try to briefly explain why. Well, if you assume MCSP is NP-hard, and this is witnessed by a one query reduction f, well, we could try doing the same thing as before. We could generate an unsat formula phi of size n and try to argue that f of phi is a hard Boolean function. But note that f is an arbitrary one query reduction. So it might be that phi is unsat and f of phi is an easy Boolean function. It might not be an M reduction, and it might flip the answer for phi. So yes instance for MCSP might correspond to no instance for SAT when the input is phi. Alternatively, we could try things the other way around, generate a satisfiable formula psi of size n, and try to argue that f of psi is a hard Boolean function, hoping that f behaves like the opposite of an M reduction. But f is an arbitrary one query reduction, and the behavior of f could depend on the input. So it could be that on the specific input psi, it behaves like an M reduction. So it could be that psi is SAT and f of psi is an easy Boolean function. So for these specific instances, phi and psi, f could behave sort of adversarially. It could act like an M reduction on psi and the opposite of an M reduction on phi, which means that we don't really get any information out of running f on these instances, any useful information in terms of circuit low bounds. So the new ingredient that we use in our results is witnessing. So we use this witnessing lemma of Goodfreund, Shalter, and Tashma. So suppose that NP doesn't equal P. What they show is that given any polynomial time algorithm that claims to solve satisfiability, there's the polynomial time algorithm B that on infinitely many input lengths outputs on input 1 to the n a small list of instances, each of polynomial size, such that the original algorithm fails to solve SAT on at least one of these instances. So if there's an algorithm that's polynomial time that fails, this is a polynomial time algorithm witnessing the failure, finding instances on which the original algorithm fails. And the result generalizes to an algorithm A running in time t, with now this witnessing algorithm running in time polynomial in t. So let me explain how to use this to handle parametric honest reductions. That's the simpler proof. So let me remind you of theorem 1. If MCSP is NP-hard in the parametric honest reductions, then E does not have polysize circuits. And the plan of the proof is as follows. Assuming the existence of a parametric honest reduction from SAT to MCSP, we define a certain polynomial time simulation A for SAT. And if the simulation succeeds on almost all inputs, then we get that NP equals P, because here's a polynomial time simulation that works on almost all inputs, and therefore SAT is in polynomial time, and so NP equals P. And from this statement that NP equals P, it follows by standard arguments that A does not have polysize circuits. So what if the simulation fails on infinitely many inputs? Then we use the witnessing lemma, and we get a polynomial time algorithm B that for infinitely many n outputs a small list of instances, of 3 instances, x, y, z, of polynomial length, such that the original simulation A fails on at least one of these. And the point now is that we'll be able to use this failure to generate a hard Boolean function. So if the simulation succeeded, we got a hard Boolean function, and if the simulation failed, then we can use the witnessing algorithm to generate a hard Boolean function, and we'll do that using the parametric honesty of the reduction. And in order to explain how, I need to tell you what the simulation is. Right? So here's the simulation A for SAT. It's very simple. We run the presumed parametric honest Turing reduction F on the input W for SAT of length n. And F, being a Turing reduction, could make several queries. Each time F makes a query, we just answer the query by yes. Trivial answer. And we keep running the Turing reduction, and at the end the Turing reduction either accepts or rejects, and we accept if only if Turing reduction accepts. Note that if our answers to queries were all correct, then by the correctness of reduction, the simulation is correct. So if each query has true answer yes, then the simulation does solve W correctly. Hence, if the simulation was to fail, at least one of the polynomially many queries made must have true answer no. And by parametric honesty of the reduction, recall that parametric honesty means that the size of the parameter is n to the omega 1, right? So if a query has, and that's the size of the parameter for any query. So if a query has answer no, then that means that that's a truth table of a Boolean function that doesn't have circuits of size n to the omega 1. And the query corresponds to a truth table of Boolean function ordo log n bits that doesn't have circuits of size n to the omega 1. So it's a truth table of Boolean function that requires exponential circuit complexity. So any query with answer no corresponds to a very hard Boolean function. And now, just by using the witnessing lemma, we have that if the simulation fails for infinitely many inputs, then infinitely often for infinitely many n, B is going to output witness triples such that at least one of them fails. But now we can just take the queries that are made on these witnesses, x, y, and z. So there's polynomially many queries that could be made in x, polynomially many queries in y, polynomially many queries in z. And we just concatenate all of these queries. And the point is, because A fails on at least one of x, y, z, that means at least one of the queries for x, y, or z must answer no, must have true answer no. And therefore that query must be the truth table of a hard Boolean function. So if you concatenate all the queries together, you get a concatenation of the truth tables of many Boolean functions, and at least one of them is very hard. But that will mean that the concatenated string is also the truth table of a hard Boolean function. So that's the argument here. And there's a lot more work required to get from parametric honest reductions to natural reductions. The proof is much more technical. And the main issue that comes up is that the parameter could be either small or large. We were really using the fact that the parameter is large for a parametric honest reduction. So now we need to deal with the case the parameter is small on some or all input lengths. And it could be the case that a simulation as defined before could fail, but the failure of the simulation won't yield any useful information because it just corresponds to queries where the parameters are small. So we need to find a way around this. And there's actually several ideas that are required. I'm not going to be able to discuss them, but just to mention that we require to use two simulations, one of which is always correct and another which can sometimes fail, but for which the failure will yield useful information. And we need to use notions from other works, such the notion of robustly often simulation. We need to exploit the parability of SAT. It gets quite technical, and I refer you to the paper. So what do these results tell us? So just to give some perspective to finish up. So we know now that to focus our efforts on showing that MCSP is NP-hard, we should perhaps be considering even weaker forms of reduction, randomized reductions, non-uniform reductions, or if we're going to use deterministic Turing reductions, reductions that use perhaps different parameters on a given input, and these parameters can't all be large because then the reduction would be parametric honest. So some parameters are small, some large. So we need to consider more complex forms of reduction. And MCSP is a fascinating problem that behaves very differently from standard NP problems, and it encodes very interesting information about circuit low bounds. So we really need to understand better to make progress in complexity theory, and results like this might perhaps help in that regard. And also much more ambitiously, perhaps results such as ours could be used to prove new circuit low bounds. So if there are quite sophisticated arguments that give from NP-hardness assumptions circuit low bounds, then perhaps one route to showing circuit low bounds is to show that MCSP is NP-hard under the kinds of reduction we consider. That's all I have to say. I hope you enjoyed this. Thanks for listening. Open problems.